Okay, so what I want to talk about today is what we're calling functions of a random variable. Okay, so kind of last time we were talking about things along the lines of, suppose I wanted to compute something like expected value of x squared, right? What I could do would be to integrate the function that I care about, so here the t squared is taking the place of x squared, against the PDF of t, and this would, or PDF of x, and then this would give me some number, right? And so the question is, more generally, just to say, if I have some function of x, I would do the same thing where I plug in the function here, and then I have the PDF of x. And again, I would get some number at the end of this, right? But there are lots of times where sometimes we care about what are the PDF and CDF of this function of a random variable, right? So, we may want to know more than just the expected value of this function. We may want to know, what are the CDF and PDF of this new random variable, right, which I could call y. And clearly, those are going to be related somehow to the CDF and PDF of x, right? Sorry, related to. Right, so we've got some original random variable, and we've got some new random variable that is created by somehow transforming x. Now we want to know, okay, so what are the new CDF and PDF of that random variable? So let me just do an example. Let's suppose that I have a uniform random variable. And then I create a new random variable y by looking at e to that random variable. And the question is, what are the CDF and the PDF of y? Now, you'll see that when I do this, usually I start out by doing the CDF first because it's easier to kind of reason about what's going on with the CDF and then take the derivative to get to the PDF. So in our case, let's kind of remind ourselves for x, the PDF looks like pretty simple. So if this is my PDF, I have basically one unit of probability mass, and that's concentrated between 0 and 1. And the CDF would look like basically, again, nothing happens before 0. And then I steadily accumulate this one unit of probability at a linear rate up until I hit 1, and then I'm done, right? So this is the PDF, this is the CDF, right? And now what I can do is I can kind of proceed along kind of first principles and say, okay, what is the CDF of y? Well, we would define that as the probability that this y is less than or equal to some value little y, right? And I'm going to plug in exactly what I told you about capital Y. It's e to the x, right? Now, I can take the log of both sides, the natural log. On this side, I have the random variable x. On this side, I have log of y, right? And now this is something that I can relate to the CDF of my original random variable, right? This is exactly what we defined as the CDF of x evaluated at log of y, okay? So on the next page, I'm going to evaluate what that is. Before I do that, let me just say that, it's usually a good idea to think about, what are the ranges of these random variables, right? So here, x ranges between 0 and 1, right? When I transform that via y, e to the 0 becomes 1, and e to the 1 becomes e, right? So I know that whatever happens, the new random variable y is really going to be active in the range 1 to e, right? So let me just kind of recall what we end up with on the last slide, right? So basically, if I go back and think about what is the CDF of x, this is like saying, well, this is going to be 0 if the log of y is less than 0. That's this region. It's going to be exactly what I put in, because this is linear, if the log of y is in the range 0 to 1, and it's going to be 1 beyond this range. And it makes more sense to think about this as, just taking, again, the exponent to both sides is like saying that when y is less than e to the 0, or 1, I get this. When y is between 1 and e, I get that. And when y is greater than e, I get this, right? So if I were to plot this, it would look something like, again, between 1 and e, I would have nothing happening before 1, and then I would have log of y, which is kind of like some sort of a curve like this, and then at e, I've topped out and I've accumulated all my probability. So this is my derived CDF, right? Now to get the PDF, what I would do is I would, take the derivative of the CDF, right? So that's by definition how we got the PDF in the first place. I take the derivative with respect to y. And so here, oops, this is a y. Here, that's pretty easy to do. So it's going to be the derivative of this, which is 1 over y, when y is in the range 1 to e. And it's going to be 0 in these flat regions. So 0 otherwise. And so if I were to draw the PDF, it would look something like this. Between 1 and e, I would have the function 1 over y. So at 1, I would have 1. At e, I would have 1 over e, which is like about a third, so it's going to drop down like this. And then it's going to be a curve like that, and 0 everywhere else. Okay? So that's the general process of doing this kind of derivation, right? And so what I did was I was able to do this pretty easily because for every value of x, there was a corresponding value of y, right? And so to be a little more explicit, what happened here? What we did was to say that if y was some invertible function of x, and I guess in this case, I also use the fact that these x and y were both positive random variables, although really invertibility is the main thing we need. Then the CDF of y is like saying, okay, what's the probability that y is less than some value? That's the probability that this function of x is less than this value. And if I can invert this function, then I have x less than or equal to the inverse value of whatever this is, and this is defined as the CDF of x evaluated at this function. So this kind of gives the direct path between the relationship between the new random variable and the old random variable CDF. And then, if I want to compute the PDF of y, I take the derivative of the CDF, which by the chain rule, right, I take the derivative of this. Well, I take the derivative of the CDF means I've got the derivative of this is the PDF of x, evaluated the same thing here, and then I have to take the derivative of whatever this function is here, right? So this is the basic, like, generalized path to how you would solve this kind of problem. Now, let's look at a special case of this. So a special case is a linear transformation. Right, what that means is that y is equal to ax plus b. Right, so for example, x is a random variable that's the temperature in Fahrenheit, and then I want to know what the random variable in Celsius is, right? That's a linear transformation. So here a and b are some constants, and I want to know what is the PDF of y. Well, again, I'm just going to follow my nose. It's the probability that ax plus b is less than or equal to y, which is equal to the probability that x is less than or equal to, I'm going to take the b over on the other side, I'm going to divide by a. Now let me just make a note here that if a is a positive number, everything is fine. if a is a negative number, when I divide both sides by the negative number, then that flips the inequality. So I have to be a little bit careful that this would turn around like this if a was less than 0. So a different way of saying this is basically like the CDF of x evaluated at this point if a is greater than 0, and this is like 1 minus the CDF of x if a is less than 0. And then if I wanted to get the PDF, I would take the derivative, right? So let's just do that. So the derivative then is going to be, again, the derivative of this xCDF is the xPDF, and then I have to take a 1 over a out of here because that's the derivative with respect to y. And if I did it the other way, I'd have negative times the PDF, again, times this 1 over a, if a is less than 0. And this I can kind of simplify and say, okay, well, actually, this is the same thing as 1 over the absolute value of a times the PDF of x. And so this is kind of related to if you're taking like signals and systems at the same time as probability. This is kind of related to the scaling and shifting of a function, right? So, for example, let's suppose that I have, y is x minus some constant. What this is saying is that, say my PDF was like this before, say it goes between like 1 and 4. This is my old PDF. Then when I shift it by b, the new ranges then are going to be like 1 minus b and 4 minus b. So what used to be 0 becomes, negative b, right? And then the PDF mass is now the same shape, but moved over by some unit, right? Similarly, if I were to scale this, let's just suppose I scale this by a constant like, 2x, for example, right? So my old PDF, let's suppose it was between 0 and 3, right, will then, according to this formula, it will become, so if this was, sorry, I'm going to crowd this page. So if this is a equals 2, this would be like saying I have 1/2 times the PDF of 1/2 y, right? So that means that my PDF is going to be the same shape, but it's going to be half as high, and it's also going to be twice as spread out, right? This is like playing the tape half as slow. And the reason for that is, right, that, now I've taken this unit of probability mass, I've spread it out over twice the area, but I need to compensate for the, so if this old height was, say, k, this new height is going to be k over 2, because the integral of this thing still has to integrate to 1, and so that's why I need to have this kind of extra scale factor. Special case of this whole linear transformation thing is a Gaussian random variable. So let me just say, let's suppose that x is Gaussian with mean mu and standard deviation sigma, and now I take that Gaussian and I do a linear transformation of it, right? So if I just apply this formula for the PDF, what I get is that the new PDF of y, well, first of all, let me just remind ourselves what was the PDF of x, right? This was something we learned about a couple lectures ago, 1 over square root of 2 pi sigma e to the minus x minus mu squared over 2 sigma squared, right? So by my formula, the new PDF is going to be 1 over this scale factor times the xPDF after it's been appropriately scaled and shifted. And I'm going to plug in, what do I get, right? So I get 1 over square root of 2 pi sigma absolute value of alpha e to the minus y minus b over a minus mu squared over 2 sigma squared. And now I'm just going to rearrange things a little bit. I'm going to note that I can say this is like, I'm just going to put parentheses around the sigma and the alpha. And then here what I have is I'm going to bring the a down into the denominator, which means I'm going to have e to the minus y minus a mu plus b squared over 2 times a sigma squared. Hopefully you're convinced that I didn't lose any terms there. And so the result is that this transformation of a Gaussian is itself Gaussian with mean a mu plus b, which kind of makes sense, and the standard deviation is basically a times the old standard deviation, right? So a linear transformation of a Gaussian is still a Gaussian, right? All I'm doing is I'm changing its position and changing its kind of squish, but I'm not changing its inherent shape, right? Okay, so this is all well and good, but things can get more complicated, right? So what if we had something more complicated than linear transformation? What about something like g of x equals x squared? Well, now we have a problem, or a potential problem, since if I look at the function x squared, like this, and again I ask myself, okay, so what is the probability that y is less than some value? That's like saying the probability that x squared is less than some value. Now the problem is that for every value of y, there are 2 values of x that could have given rise to it, okay? And so if I kind of shade in for this event, probability of y less than y, what is the corresponding event in x, right? And this is the way that I think is always useful to solve these problems. I say, okay, what's the probability that I'm in this region on, so this is my x, this is my y, right? So what's the probability that I'm in this region here? I trace over to what is the corresponding region in x where that occurred, right? And so that would be like saying what's going on in this region on the x-axis. This value here is plus square root of y. This value here is minus square root of y, right? So the equivalent event in x is like saying what's the probability that x is in this range, right? Which would be like saying I take the CDF of x at plus square root of y and I subtract the CDF of x at minus square root of y, right? And this is only if y is itself a positive number, right? If y is negative, I get nothing, right? Because y has to be positive in the first place. So this would be my, new CDF, and then consequently my PDF would be the derivative of this, which is going to be the derivative of the CDF is the PDF times the derivative of this function, which is going to be 1/2 over square root of y. And then I have another term here, which is minus this thing evaluated at minus square root of y times the derivative of this, which is minus 1 over 2 square root of y. So these two things basically cancel out. What I get is 1 over 2 square root of y times the sum of these two PDF chunks. Again, and this is only for positive values of y. Okay. So for example, let's apply this to taking the square of a Gaussian random variable, for example. So let's suppose that x is Gaussian with mean 0 and standard deviation 1, and y is equal to x squared, right? And I want to know what is the PDF of y. Well, I'm just going to apply this formula down here directly, right? It's going to be 1 over 2 square root of y times the Gaussian random variable applied. So I'm going to have a 1 over 2, I'm sorry, 1 over 2 square root 2 pi sigma, and then I'm going to have actually, sorry, let's try this again. So let's just remind ourselves, what is the PDF of x here? The PDF of x is 1 over square root of 2 pi e to the minus x squared over 2. Pretty simple because this is just a simple Gaussian, right? So my PDF of y is going to be 1 over 2 square root of y, and then I'm going to evaluate this thing at plus square root of y, so I get e to the minus y over 2, and then I get this thing evaluated at minus square root of y, which turns out to be the same thing. So putting it all together, I get a factor of 2 cancels out this factor of 2. What I get is 1 over square root of 2 pi y e to the minus y over 2. And again, this is only when y is greater than 0, 0 else. And so this thing here is basically, now we've derived a new type of random variable. This is actually called a chi-square. Sometimes you see it with this kind of Greek letter chi random variable with 1 degree of freedom. And so if you look in a textbook or online, you can certainly find out that the chi-squared, similar to something like the exponential or the gamma beta variables, it's basically like a random variable where you have some parameters that you can choose, and this happens to be what you'd get if you plugged in 1 degree of freedom for that. Okay, so this is a new kind of random variable. So you can take this general idea, right, where I have a many-to-one mapping of x to y to deal with other more complicated functions, right? So let's suppose instead that my function was like the absolute value of x, right? Then my function would look like a V shape, like this. And if I want to know what is the CDF going to look like, again, I kind of shade in, okay, here's y, here's that event, and then where is it on the, x-axis? So here, I'm looking at this event in x that goes from minus y to plus y, right? So in this case, it would be the CDF of x evaluated at plus y minus CDF of x evaluated at minus y, and again, this would only apply at y greater than or equal to 0, and in the same way, the PDF would look like the derivative, which is pretty easy to take in this case, and so on. We could get a little more fancy with this if you wanted to. So, a lot of times in electrical engineering, you have situations like, so common in electrical engineering, or like things like audio signals. You could have something like a limiter that basically says, okay, I pass through the signal up to some sort of amplitude, and then I basically clip it to a certain range. So this is what's called a limiter. Or you could have something that's called a blanker, which basically says, okay, linearly pass everything through at a certain point, and then if you're above a certain range, just zero it out, right? This is like a blanker. Taking the absolute value of something is kind of like a rectifier. Or I could do something like, take only the positive part of the signal, right? So this is like something like g of x equals kind of like x, the positive part. Now, in any of these cases where you have kind of like a hard threshold, or where you've got kind of a discontinuity in the function, or not discontinuity, but any sort of like switch in the function, basically, you're going to have the potential to introduce kind of like one of those weird mixed PDFs that we talked about in previous lectures, right? So for example, let's consider what would happen here, right? So let's suppose that if we have just give me x if x is greater than 0, and give me 0 if x is less than or equal to 0, right? So what would the PDF be here? So here, this is kind of like a pathological case where, again, it's mostly one-to-one, but here there are many values of x that map onto y equals 0, right? And so what could happen is that at y equals 0, we have basically all this probability mass of all the stuff happening here. This whole event gets lumped into the y equals 0 region. So this is like saying, okay, well, if x is greater than 0, life is good. If y is less than 0, then I get nothing, right? Because I don't allow that to even happen. And I guess actually I should be a little bit clearer. No, this is okay. Okay, so this is basically like saying I get the CDF when y is greater than 0, and I get 0 when y is less than 0. So if I look at the old CDF of x, right, the old CDF of x could have some, stuff over here in the negative world, and I climb up to 1, right? This is like the old CDF. And so that means that this whole mass up here, up to the point, the CDF evaluated at 0, all that stuff is going to get lumped into the, the probability of things happening at 0. So the new CDF is going to look like nothing here, and then there's going to be a hop up to whatever this value was, and then I'm going to have a climb up to 0. So there's a step function in the new CDF, which means that when I take the derivative of this, I'm going to have part of it is okay out here, but then part of it is going to be like a delta function that comes from the step. So the PDF is kind of a mixed type, in the sense that if I take the derivative of that CDF, I'm going to have a delta function at 0, which is the same height as all the stuff that happened up to 0, and then I'm going to have whatever the derivative of the PDF was over here. This is kind of like the, the PDF of x times, the step function that turns on 0. So whatever happened over here, I don't care about. So it's kind of like a weird, a weird function, right? It's stuff that, again, I wouldn't actually ever ask a lot of questions about this, but this is the kind of thing that, it could happen, and I think it's just good to be careful about what might happen. So finally, the last thing I want to say on this issue is that things can get even more complicated if basically for many to one mappings, we could have even more terms. So for example, what we talked about in the x squared case was kind of like a 2-to-1 mapping, right? Where for every value of y, there were 2 values of x, right? But what would happen if I had something that was even crazier, right? So let's suppose that I would have something like, some really weird function of x, right? And now I ask, okay, what's the probability that I am less than this value here, right? Less than y. What is that event in x? Well, life could be really weird, right? So I'd have to kind of think about, okay, I take that dividing line, and then I have, a region out this way, like I've got one event in x here, and I've got like another event in x here, and I've got another event in x out here. So I could have, and of course, if I were to raise the water level, right? So if I were to raise the water level to here, suddenly I'd have another disconnected piece. It could be like a nightmare, right? So I'm not going to go into this a whole lot, except to say that, generally, if, if I have a set of values satisfy that these are the values that map to some given value y, then the PDF of y at that point looks like the sum of the values of the PDF of x evaluated at these points times a piece that comes from the derivative of this from the chain rule, right? So this is just kind of like a generalization of the k equals 2 case that we used, for example, to get the chi-squared random variable, right? So not a huge deal. I don't want to spend a lot of time on this, but that's the idea, okay? Okay, last thing I want to say in this topic is switching gears a little bit to talk about a couple of useful inequalities. And these are kind of fun because it makes you think about, okay, so suppose I didn't have very much information at all about a random variable. Is there still a conclusion I can draw about its probabilistic behavior? So, for example, say we only know that x is non-negative with mean mu. Can we say anything about this event, that probability of x is greater than or equal to a? Right? So it seems like maybe on the face of it, it's difficult to say anything, right? So suppose I tell you, okay, this random variable has mean 3. What's the probability that's greater than 50, right? How could I say? Well, let's think about this for a second. So what I want to do is I want to derive, okay, this mu is the expected value of x, which is this integral, right? I know this is a positive random variable, so I can just integrate it from 0 to infinity, okay? And now I can say, well, this integral is, since everything is positive here, is at least as much as if I were to choose to start the integral at some value a, okay? So that's definitely true. And this is true for any positive value of a. Now I say, okay, well, inside this integral, all these values of x are at least equal to a, right? So I can put a further bound by saying this is at least, it's certainly at least as much as a times this integral. And now I can pull the a out of here. This is nothing more than the probability, this is a times the probability that x is greater than or equal to a. So what did I learn? I basically chose an arbitrary positive value of a, and then I derived a bound on this probability. So if I rearrange things, I get what's called the Markov Inequality, which says that under those conditions of x being a non-negative random variable, the probability of x being greater than some value is no more than the mean over a. Okay? Which is kind of a neat result, right? That's like saying that no matter, what's going on over here in the PDF, I can bound how much probability is in this tail, okay? And so here's an example. Suppose I have a router that will crash if it receives more than 1,000 packets a second. I do some measurements of my traffic. I measure the average load is 5 packets a second, or say 50 packets a second. So, can I estimate the probability that the router crashes? Well, the probability of a crash is like saying, what's the probability that I get more than 1,000 packets? which by the Markov inequality is got to be less than the mean 50 over the number I'm asking about, 1,000, which is 0.05, right? So I can see that I don't have to know anything about the PDF to be able to say something useful about the probability of a crash, right? So the problem with this is that, the actual probability, depending on the value, the true PDF, could be much lower than this, right? So here is a kind of a crazy example, right? So let's suppose that I say that the average height of a kid in kindergarten is 3.5 feet, okay? And then I want to know what is the probability that if I choose a child, that child is greater than 9 feet tall, right? Well, Markov would be able to tell me that this probability is bounded by 3.5 over 9, which is equal to, 0.389, right? So clearly my probability is much, 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 much less than this, right? And the bound is valid, but it's not what's called a tight bound. So the Markov bound can be very loose, meaning that this number could be much bigger than the actual probability. So we can get a tighter bound the more we know about the PDF. So we can get a tighter bound if we also know the standard deviation, for example. Okay. Or the variance, if you like it better. Okay. So let's look at this. So let's suppose that let's let y equal x minus the mean squared. Okay. So the expected value of this is exactly what we defined as the variance, right? And now if I apply the Markov inequality to this is like saying, what is the probability that y is greater than some positive value a squared? Well, that's less than the expected value of y over the mean, or over the value I care about, which is equal to sigma squared over a squared, or sigma over a squared. Okay? And if I plug back in what I learned, this is like saying the probability that x minus mu squared is greater than or equal to a squared is less than or equal to sigma over a squared. If I take away the squares over this side, this is the same thing as saying the probability that I am more than a away from the mean. So this is in some sense a kind of a bound on how far could I possibly be away from the mean. This is called the Chebyshev inequality. Right? So if I wanted to apply this to my example with the kindergartners, I need to tell you also some sort of information about the variance, right? So I could say, suppose also that the standard deviation of the heights of the kids in the kindergarten is half a foot, right? Now I can say, okay, what's the probability that x is greater than 9 feet? That's going to be basically less than or equal to the probability that x minus the mean of 3.5 feet is greater than 5.5 feet, which by the Chebyshev inequality is the standard deviation over this number squared, right? So this is 5, this is 1/2, this is 11/2, this is like 1 over 11 squared, which is equal to 0.0008, right? So this is a much tighter bound on this probability that I got before, right? And in fact, I could probably even make this smaller because I'm kind of saying, okay, if I have 3.5 feet, I'm kind of taking whatever distribution I have and I'm asking, okay, what's the probability that I'm further than 5.5 feet. So this is actually like -2. So I'm kind of, this is a bound on what's in both of these tails. That's why I said that, actually this is just one of the tails. If I assume that things were symmetric, I could even just chop this off by a half, right? So if the distribution is known to be symmetric, then I could look at the Chebyshev bound over 2, which would be equal to even less, right? And of course, then, if I had access to the full distribution, I would be able to compute the actual probability. So the more I know, the better I can do, right? But even when I don't know very much at all, I can still get some useful information. Okay, so that's about the end of the part of the book and about the material that's about one random variable. The next thing we're going to talk about is what happens when I have two random variables, right? That may be related to each other, issues like correlation, independence, and so on will come into play when we have two random variables at once. So that's going to be the topic of the next lecture. Okay, and I will see you next time.